If you're dereferencing an integer, that means that you have a reference to an integer. So that means that array is a reference to an integer. So that means ARR2 star is an int type, like dereference of array2 is an integer, which means that array2 is really a reference to an integer. And there's other ways to do dereferences. Does anyone know the two other common ways that we use that we can dereference values in C? The ampersand. Does the ampersand dereference something? The ampersand is similar to the star, but it actually doesn't dereference. It does what? Yeah? So does it save the value? It doesn't really save this value. What's the opposite of value? The address. It gets the address. The ampersand gets the address. It's kind of the opposite of a dereference. The ampersand is really a reference operator. The idea is that you're acquiring the reference to this value. You're finding out where this thing is stored at. You're finding the address. So the star kind of takes you from the address and it takes you into the value. The ampersand takes you kind of from the value and takes you to the address. So they're like kind of opposites of each other. So there's another operator, and I know that you guys have used this in all of your C classes. You use them all the time when you use an array. What do you use when you use an array? The brackets. The brackets is an example of a dereference operation. The brackets will go to some location in memory and will acquire the value at that location, which is why all your arrays are really addresses, because they are some pointer to some section of memory, and those brackets will follow the address to that location and grab the value out. So another dereference operator is bracket. But normally you have to supply some number to it. You like do bracket 0 or something like that. It turns out bracket 0 is the exact same as star. These two are equivalent to each other. They just kind of put in different locations. One you do star array, the other one you do like array bracket 0. Those will actually get you the same value. All right, and then there's one more dereference operator, and it's specific to structs. I'll give you a hint. Yeah, the arrow. The arrow is another example of a dereference operator. It will dereference and then acquire the member of something, but it is a way to do a dereference. So we also have this thing here, another dereference operator, but it's like struct exclusive. And I'll hopefully be able to go over that a little bit more today. All right, is there any questions about this refresher on C before we begin? Yeah.
So, if you use a double, we didn't really go over this.
That's fine.
But like double pointers?
Yeah.
Is it just literally like a pointer pointing so that pointer
Yep.
points to like values?
Yes. So the idea is that a 2D double pointer, or like an int star as an example, that means that you have some address, and if you follow that address to its value, it actually is going to be another address. And when you follow that address to its value, it becomes whatever the type you're looking for. So if it's an int star, if you follow it once, you get an address. If you follow it again, you end up with now an integer. Or really, if you dereference it once, you end up with an int star, because you originally had an int reference. And so by dereferencing it once, now it becomes just a regular int reference. And then by dereferencing it again, it becomes a regular integer. So when you do like a 2D array, and you like do bracket 0 or bracket I, bracket j, you're really kind of applying the star twice. And so you're getting in, like if you have a 2D array, you really have like a reference like an int star. And then by doing the bracket, you're dereferencing twice, and you're going to the value at that point. Good question. Is there any other questions before we begin? No? Okay, well, it's good. Oh wait, I wanted to finish this example. Let me finish this example, and then I'll continue that thought, because it's a good one. So what I want to do is I wanted to create this dynamically. We're creating an integer reference by doing the star here, and what we can now do is do array2 is equal to int star, and now we're saying that it's going to be a integer reference type. That's what this cast is for. It's saying that this matches this, which is good. If that didn't match, that would be bad. But because int star here is the array2, we can say array2 is equal to the int star, and we won't have a problem here. We do Malloc, we do 10, size of int. All right, and then ideally we would want to do a free here at some point before we exit. Do we need a free array? No, it's statically created. Please don't free it. All right. And then this is like the correct way. Correct. All right. Yeah. All right. So that's fun. Let's go ahead and take a look at how we can do two-dimensional memory dynamically. And we're going to do exactly what you mentioned, which is we're going to do a pointer, or double pointer. And we're going to use that to go ahead and create an array of arrays. So, when you actually have an array, yeah.
I forgot if you already said this, but can you explain it again why you passed the Malloc?
Why did I cast the calloc? It's not required in C, but the idea is it's kind of required in like C++. You're just telling the program that this is a void pointer, but I needed you to actually make it into this other pointer because that's what I'm trying to store this into. And so you're like explicitly casting it into the thing that we're storing in. C can do some implicit casting. C++ doesn't like doing that without like maybe some extra flags turned on when you're compiling. I don't know actually if you can actually just compile without casting in C++. I've never tried doing it. It's something that like you should do. It's basically just assuring the thing that's going to be executing your code that this is the type you're looking for. But it's not something you should just do willy-nilly. I recommend doing it only when you're sure that it will work. There's a lot of people that try to do that to turn one type into another, and that's very, very dangerous. You should only be doing it like when you're turning a void pointer into another pointer type. There's probably other uses for it, but I never use it. So you probably won't need to use it either. All right, but let's go ahead and I'm just going to close that so I don't get tempted to play around with it. Let's talk about 2D array. So 2D arrays in terms of dynamic memory. So when you're doing static memory, you don't really have like an array of pointers. Like if you do like int grid bracket 10 bracket 10, it's actually stored all kind of in one contiguous section of memory. And the idea is that they use some offsetting to go ahead and jump across the different like rows of your grid. And they use like the size of like static arrays of size 10 to go ahead and figure out how many times it needs to jump to get to its proper location. So it's more like a single dimensional array in my opinion when you're using the static memory, but this is going to be proper 2D like array of pointers sort of behavior when we're doing the dynamic memory version of the 2D array. I don't really want to get into too much detail as to like how the static memory works for 2D arrays. We really should have been covered in your intro to C class, and we don't test it on the foundation exam, I'm pretty sure. But like we don't ask you like to explain the workings of it. So I'm going to go ahead and kind of assume that you guys all have the memory, the knowledge of it, at least enough knowledge to know like how you can access like something that's in a spot like IJ. And all I'm going to do is I'm going to focus on how we can go ahead and do this from the dynamic memory perspective. So how we actually do this is we normally go ahead and do whatever type we're looking for. And then of course we do star, star, and then like our variable name. And this is it. This is how you begin the declaration of what's going to hopefully be a 2D section of memory. All right, so let's just see an example of what this would look like. We would do something like int star star, and then we would say grid. There you go. Perfect, reasonable example of the creation of the beginning of a two-dimensional section of memory. So now the question is, well, how do we go ahead and actually create this grid dynamically? Like, suppose that I want to go ahead and make this a Sudoku board. Sudoku boards are 9x9, they're pretty easy. Like maybe let's not do a Sudoku board. Let's do something that's like a little more oblong. What's an example of like an oblong board shape? Did anyone play games? No? Yeah? What kind of games? That's, you know what? Let me go ahead and I'll try doing something a little bit different. Man, everything I keep thinking of is like square, because I'm thinking of chess, I'm thinking of Go, I'm thinking of Shoji. Like all these guys are like just square grids. All right, whatever. We'll just do Sudoku because Sudoku is like easy. We'll worry about like maybe better examples later. Oh, Venero. Venero is non-square. Oh well. we'll just go ahead and work with the Sudoku board. So we're going to go ahead and try to create a Sudoku board out of this. So this is going to be a Sudoku example. So what we want to do is, if you know what a Sudoku board looks like, it's a 9x9 grid. So the idea is we have like this square. I'm not going to draw everything out. I don't even know if I did 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh wow, I did. Okay, cool. Well, like obviously there's not 9 here. So in terms of like your computer has an array, like can do arrays. And arrays is kind of like a linear section of memory. But we're not trying to do a linear section here. We're trying to do like a linear on top of a linear on top of a linear on top of a linear. And really we need to be able to kind of like have 2 ways to access it. It's not just like we need a single index. I mean, I guess you could do a single index if you want, but really we would want something where it's like we have 2 indices. One is representing like the row information, and the other one is representing kind of the column information. Like I think you would agree that like when you play Battleship, you have something like B5 or something like that, and that like corresponds to like what row you're in and what column of that row you're at. So if I said something like the 3rd row, 5th column, like where would that be at in this picture? So like this is 1, 2, 3. Like assuming that we one index because we're normal human beings and not computer scientists, it'd be 1, 2, 3, and this would be 1, 2, 3, 4, 5. So it'd be like at this X location here. So what we need to do is we need to be able to go ahead and have something that says like we have to know kind of like where our rows are at, and then once we get into the row, we can go ahead and like hopefully like move over some amount to get into the correct column. So it's easy to think about it if we had just a single row. If we have just a single row is really what? If we have just a single row in Sudoku, yeah, this could be stored like using an array. So 1 row is like an array, right? But we don't want to store 1 row, right? What are we really trying to store here? Like 9 rows. We want a collection of rows. We want multiple rows. And how do we normally store multiple of some data type in C? An array. And so that's what we're going to use here, is we're going to create an array, and that array will go ahead and inside each one of those will be themselves an array. So if we imagine pictorially what we speak about, so this could have values in it, like maybe it's like 9, 8, 3, 2, 7, 4, 2. I don't know how to play Sudoku, so this is probably what I would actually write up. And if you know Sudoku, you know this is obviously not good. But the idea is, so this would be like a single row, but we need to be able to get information as to where this row is at. So what we need is like an additional array on top of this that'll go ahead and point us to this row as well. And so if this is in theory like the 3rd row, like at our 3rd spot of our array, we need to point to this memory address here. So what we need is we need some way to go ahead and go from this spot here to this location. And this is obviously going to be some address. But again, how arrays work in C is they're really themselves a pointer. And so what we're going to have kind of in our main function, our grid itself is going to have like some pointer to this section of memory. So we have a pointer that's at this memory location is going to point to values, but like every consecutive spot is also going to point to other memory sections, and each of those spots like that are like being pointed to the second time are going to be really like going to hold an entire row of our form. So we only need 2 references though, because like from grid we're going to go to our array of pointers, and then we're going to follow that to where our values are going to be stored at. So let's go ahead and then create this, hopefully. So what do we need to do to allocate the memory for grid? Like what thoughts do you guys have? Like what would be good to go ahead and create this behavior? All right, calloc, and what am I going to do with calloc? How am I going to use calloc here?
Grid equals int double-star?
Yep.
Okay, and then calloc, and then we're going to add parentheses 9, and then size of integer star.
Very good. So we're creating 9 integer pointers because every single one of these spots in this array we're creating, it has to be a pointer to some array of integers. So what we're going to do is we're going to go ahead and make sure every element we're creating is going to be the size of that int star. We want 9 of them because that's how big a Sudoku board is. And of course, since grid is of the type int star star, we're going to hash to that type, and that will go ahead and store our information. So that's perfect. Thank you. Then how do I create each of the rows? Because all I did was I kind of created like the spot, the addresses for each row, but I didn't actually create the rows themselves. So what do I need to do extra? So, does not create individual rows. We need to do something else. Yes, we're going to do a loop, and then what do we want to do inside that loop? How much do we want to loop? We're going to loop up to 9, so we're going to do int I is equal to 0, I is less than 9, I plus plus. And what are we going to do in this loop? We have to actually do another set of allocation here. So what's that going to be? Int star? Is that how I want to begin? Maybe, we'll see. So int star what? Calc 9 size of I. Are we sure I? Is I a type? Like, technically size of I works, but we really should only be, it's a good practice to only pass in types into size of. And so because the I is not actually a type, it's actually a variable, it is of int type. In theory, it should actually work, but it's actually more appropriate to use size of int here. And now you're wondering, well, then what am I doing wrong then? I should probably be using I here somewhere. And the answer is yes, we should be using I. So the thing is, we're creating, what is this creating here? Well, I'm going to put that there, it might make more sense. What am I creating at this point? I'm creating, well, what would this normally create for us? Yeah, in the back?
It'll create a row the size of whatever I is at.
So we're creating a row. What is a row though? It is like in C terms.
It's
An
just
array. Yeah, so we're creating an array of size 9, and what does calc give us? Calc gives us what when it creates that information? It gives us a void pointer, or really the address, right? So it's giving us that address, and the thing is, we're not storing that address. Because we're not storing that address, what do you think is going to happen here? If we don't have access to that memory, and we've created it and like we said, protect this for our computer, we need it, what's going to happen to us? We're going to create a memory leak here. Yeah, this actually memory leaks. And the reason why is because we're not holding on to this pointer. So we need to hold on to this. Like, where could we possibly store this?
Grid bracket I.
Yeah. We want to do grid bracket I. And this is like the worst formatting. Please don't do this. Like have indentation. But like I wanted to go ahead and just kind of like do this so that way I can go ahead and kind of express like the problems that we end up running into. So this would be, is this correct? Is it proper to say grid I is equal to int star? And isn't grid a star star? Yeah, so is it okay if I do this? And if so, why?
Yeah, because you're doing it for each value, so like grid 1, grid 2.
So what I want to know is grid of I of type int star?
Yes.
And over there?
Yes,
Yeah, why?
because we declared grid as star star.
Okay.
Reference it becomes grid star.
Good. Yes. So because we're dereferencing it here, and it's already a double reference, by dereferencing it once, it loses one of its stars. It becomes just a normal int star here, and so that's why I'm able to do this assignment. Because grid is a star star, by doing this bracket of I here, we remove one of those stars and we're left with just a regular int star here. And an int star is an int pointer, and hopefully you kind of like think to yourself, int pointers are really kind of like an int array, and so this is going to be an array of values that we have going on. And like grid I is really an array of integers, while grid is an array of integers. All right, and now in theory you can do whatever you want with the Sudoku board. What you should not do this. So this is like good. And I sometimes people see them do this, and I just want to kind of like emphasize that this is not good. Or int j is equal to 0, j is less than 9, j plus plus. And then you do something like grid of I of j is equal to like int calc 1 comma size of int. All right, what issues do we have with this thing here? Any thoughts? Yeah. Overlapping? Okay. Yes, kind of, but that's not exactly the error I was looking for. I'd probably end up giving that points on a test. Probably not full credit because I need a little bit more explanation. Like, what memory violation do we end up getting by doing this? There is going to be maybe some overlap issue in a weird way. Yeah, in the middle.
A memory leak
Memory leak. Why is there going to be a memory leak here?
is the integer, or there's no int star here.
Yeah, there's no reference. We don't have the ability. Grid of ij is not a reference, right? Grid of ij, we've removed both of those references. It's now an int. And so what we're trying to do is we're trying to store, well, first of all, you shouldn't even be casting a void star to an int. That's like already very problematic. But we're trying to store an address into an integer. And I mentioned at the beginning, if you have like a system where your ints are very small, what's going to happen is you're not going to be able to store the whole address, and you're not going to be able to find that section of memory to free it in the end. So this is going to cause a memory leak. Also, this is a type error. Please don't do this. Not good. This is bad. No. Leak. Bad.
What is that part that they're trying to do?
So some people think that they need to create each individual int in the 2D grid. You don't need to do that because this thing here created all the integers for you. It created all 9 integers. So we already did size of int, so we already created the integers. There's no reason to do this. But I see people do this all the time on tests and quizzes and on foundation exams. Do not do this. You will definitely lose points. And if not on the foundation exam, then definitely on my test you'll lose points if you do this. All right, so I'm just gonna like even X this out so that way people hopefully that are reading this notes later don't think that's the important thing to do. All right, so now the question becomes, you created a grid. What are you gonna do with it now that your program is exiting? Free it. Okay, how are we gonna free it? So let's imagine we created this grid, and now what we need to do, this grid here, and now I need to free it, so I just do something like free grid, and everything's good, right? All right, what's the problem? Yeah? Well, the grid actually does point to the section of memory, right? It is a reference to a reference of integers, which means that freeing it is not a bad thing. If we look, grid actually is being created dynamically. It's going to hold an address, and freeing it is a good thing. You always want to make sure that you free whatever you Malloc or Malloc. There's 2 hands up. I'll go with the back one though. Yeah.
Read each individual part of that
Is- Oh, okay, very good. You got to the point that I wanted to bring up. You got both of them. So we need to free everything, and you might be tempted to do, okay, like we need to free each individual Malloc we've done. For int I is equal to 0, I is less than 9, I plus plus. And then you're tempted to say, okay, free grid of I. But you said that this was the wrong thing to do. Why is this the wrong thing to do? Does someone want to tell me why this is wrong? Yeah. Yes, very good. We're dereferencing grid. We're dereferencing grid here. What's the problem with dereferencing grid here? So we're dereferencing grid, but what did we do to grid earlier? We freed it. So what we did is we told the computer, you can have this memory back, do whatever you need to do to it. I don't need it anymore. And then what we did is we turned right around and began using it. This is known as a what? We are using it after, what did we do? Use after, yeah? Use after free. This is undefined behavior. Don't do it. It's also bad. So what the proper thing to do is we cannot use this grid if we've already freed it. So what we need to do instead is move this down here instead. So if we move the grid below, like the free grid below, then that means we'll free all the parts using grid. And then once we freed all the parts using grid, we can now get rid of grid because it's no longer necessary. So like this is unfortunately the wrong order. What the proper thing to do is something like for int I is equal to 0, I is less than 9, I plus plus, and then you do free grid of I, and then down here you would, free grid, and that's it. This is correct. All right. So what if we had a three-dimensional array? So what would a 3D array look like? Like int star star star. So this is a 3D example. And this will like kind of extend to like multiple dimensions. But I'll show the 3 dimensionals before we move on. So this will be big array. I don't know what you're doing with 3 dimensions. I hope you know what you're doing. Like 3 dimensions is useful, but like it doesn't come up very often. So yeah.
Is there 3-dimensional arrays on the foundation kit?
There could be. Thanks. Yeah, there could very easily be 3-dimensional arrays on the foundation exam. They might even say, hey, we've created this 3-dimensional array dynamically, free it for us. And so you'll have to write the code that we're going to be going through in a moment. I don't know if that's what's going to happen. We don't write those problems normally until like a week before the exam starts. Not really a week before, it's normally like a month before. But that means it's not going to happen for some time. All right, so let's go ahead and take a look as to what's going to happen here. So allocation, I'm just going to go ahead and make it a symbol thing. I'm going to make it like, we'll do the first dimension is like, we'll do like 100, and then we'll do the second dimension is like of size 10, and then we'll do the third dimension, I'll do of size 3. So this is like not necessary to do dynamically. You can do this statically with like, you know, very easily stuff. What's nice is about multi-dimensional things, especially with dynamic memory, is you don't have to have them all be the same size. You can go ahead and have them vary in sizes depending on like what you're working with. And maybe I'll do an example of that, like in class when we get close to the exam, or if I'm nice, like next time. Because now we've talked about QD, but I can go ahead and give you a warm-up question on that. But for this case, we're going to go ahead and just work with really simple stuff, just so that way we can get like a better feel for it. So I'm going to go through the allocation, and then I'll go through the freeing. So we want to do something like big array is equal to int star star star, because it's a 3D array. We're going to do calc, and we're going to do 100, comma, size of, what's going to go in here? Anyone? Int star star, I heard someone say it. All right, and that's because we want to make 100 things that are all going to be 2 references basically for an integer or 2D arrays. And now what we need to do is we need to create all 100 of these guys. So you want to do something like for int I is equal to 0, I is less than what? What do I want to do? I is less than here? 100. And then I plus plus. And we want to say big array of position I is equal to what? So finish this one for me. So parentheses what? Int star star. Very good. Then what? Calc. Now 10, comma, size of int star. All right. And now what do I need to do? Thoughts? Yeah. We're going to do another for loop. Where do I want to do it? Do I want to do it here? I want to do it in this for loop. Thanks. So what we want to do is we want to do an allocation here. And the reason why is because we want to, for every I, we want to go through every j and then do the allocation. Very good. So we're going to do for int j is equal to 0. J is less than what this time? 10. And then what do I want to do? J plus plus. Now what? I did not give myself enough room. Is there anything I want to do here? Yeah? Big ARR of J? Are you sure? All right, we actually need to do something else first. What do we need to do? Yeah, in the back?
array I of j?
Yeah, we need to do I, J. We need both of them. This is an I, and this is a J. So we need to do both of them because we need to make sure that we dereference this thing twice on this layer to go ahead and begin doing the assignment. Because what we're going to do here, what's going to be the stuff that happens on the other side of this? What do we want to put over here? You want to say this is equal to something. What's this going to be equal to? Int star. And so if this is an int star, big array is a triple star. And so because this is going to be a single star here, I need to dereference twice here. I need to get rid of 2 of those stars. So I need to use 2 dereferences here. I need to use brackets twice in order to make sure that this is going to work out properly. So that's why I need both I and J. And really what you can imagine is that we have basically 100 by 10 units of something. And what I need to do is I need to go into the, like one of the or maybe it's like 100 by 10, depending how you think about it. We need to go into like every row, and in every row we need to go to every column. And so we need to go basically to the ith jth position, and then we need to do an allocation in the 3rd dimension. So we need to make like kind of like a depth to this like weird like block of memory that we have going on. All right. So what do we want to do over here? Calc. All right. Now what? 3. Why 3? That's the dimension of the 3rd depth, of the 3rd size or whatever. And then what do I want to do? Size of it. So maybe these are like points in 3-dimensional space, and you have like a set of 100, and each like set has 10 elements in them. I don't know. There's probably some reason you'd want to do this, but I want to go ahead and point something out that's like kind of minor. We actually end up creating a lot more memory by doing the things that are larger first. So by doing this larger thing here, we're creating actually 100 pointers, and then we have basically 100 times 10 pointers. So we have like 1,000 pointers that we're creating. Like in this level here, we have like 1,000 of them. So the thing is, like, if we're creating 100 and then 1,000 here, we're creating really like not 100,000, but we're creating like 1,100 pointers. If we had done it where this was 3, this was 10, and this was 100, then we'd be creating 3 pointers plus 3 times 10, or really 3 pointers here, and then plus 3 times 10, which is going to be 30. So we'd be using only 33 pointers instead. So actually, by using this biggest number first, we're actually creating more memory than if we were to do it the other way, where we start with the 3 at the highest level, and then working our way down. So if you're doing dynamic memory, if you are actually concerned about the number of allocations you're creating, and you're concerned about like the number of extra memory you're creating by using these pointers, you want to go ahead and start by using your smallest dimension as your first one, and then working your way down that way. Kind of a silly thing to mention. It doesn't come up very often. Maybe like if you're like creating a whole bunch of values that can be like really important. Like if you're creating like a whole bunch of points that are like 2-dimension, it might be better to go ahead and create basically an array of x's and an array of y's instead of like doing an array of points, each of one as both an x and a y. Very, very strange. It happens. It comes up a lot in competitive programming. For those of you that are interested in it, if you're doing like allocation, it's better to go ahead and do your allocations in the other way. All right, so we created this memory. Now let's free it up. So let's do that. So to free it, how do we want to free it? Do we want to start with saying free big array?
No.
No. Okay, so what do we want to start with saying?
4.
Or? Yes. Yep. All right, that's the good start. Now what do we do? Do we free big array at position 9? In the back?
You do another for loop?
Yes, we want to start the other for loop down. Why do we not want to free a big array of I right now? Does anyone want to tell me why it's a bad idea to free big array of I? Yeah, the front. Yeah, so it's undefined behavior if we free big array of I now, and then end up freeing big array of ij later. So we want to make sure we free big array of ij now because ij was allocated. We want to make sure we get that free going on before we try to do this free. So we need to do for int j is equal to 0, j is less than 10, j plus plus, and then we say free big array at position I, j. Again, for every free that you create for every allocation you create up here, you want to typically do a corresponding free down here. I'm just going to put brackets in here so it's a little bit more readable. I forgot to put my closing sorry, brace there, so there, that's complete now. But then back to this example, and if you want to, you can go ahead and like set big array of ij to null, so that way you check if you dereference null, but I'm not going to do that because it's going to create a lot of extra like stuff I'm writing out. So after we do this free, what do we want to do? What's the next step? What do we want to put? Do you want to put bracket here? Curly brace? In the back?
You free big array of I.
We want a free big array of I. We can free big array of I now because we completely used array of I. It's no longer needed anymore. All right, and now what do we do? Yep. So, for like kind of a rule of thumb, normally your allocations happen in the reverse order of your frees. So you get kind of like this mirror behavior where we start like kind of the level that's like the deepest, or like maybe the shallowest. Yeah, this is like the shallowest level. And then we get deeper and deeper with your allocations. Here we start at the deepest level and we get shallower and shallower. So it's like we work our way down and then we have to work our way back up. Is that good? Does that make sense? All right. Good rule of thumb, and you guys are probably not going to remember for the foundation exam. At least the people that aren't here are going to remember it for the foundation exam. All right. So that's it for the three-dimensional example. This is like 3D, free. All right. So let's talk now about, that's all I wrote, 3D, free exam. All right. So let's talk now about structures. So sometimes when you do dynamic memory stuff, you want to actually create structures. It's really not that hard to create structures dynamic memory-wise. So what I'm going to do is I'm going to show you a very simple way that we can go ahead and use dynamic memory with our structures. So maybe I want to do something simple, like I want to create an array of students. Every student will have a corresponding name, but maybe I'll create a structure because students like have like maybe some grade information as well. So what we're going to do, I'm pulling this chair over. Oh god, I don't like this chair. I've been standing for too long. So what we're going to do is we're going to create a student. And the student structure will have like both like maybe a grade, like a GPA, I don't know, and then like a name. And the name will be like some sequence of characters. So what we can do is we can say, let's say struct student. And hopefully you remember like creating these inside your Intro to C class. And then we do something like double or float, I cannot spell, double, there you go, GPA. And then we can do char name. If I want to make this dynamically, I have to do a star there. And so rather than like creating a whole bunch of memory for each of my students, what I can do is I can go ahead and just create the name however big it needs to be for each student. So that way I like have like some memory saving behavior here. All right. And now like let's imagine I want to create an array of students. Each student like we'll have like 250 of them. And then we'll have to like allocate each student afterwards. So what we're going to do is say, so struct, this is the example of structure allocations. So we use struct, students, and like where do I put the star at? Do I put the star here? If I'm trying to create an array of students? The after student? Don't we normally put the star there before the variable name? Is this the variable name? No, this is the type still. It is a struct student. That is the type that we're working with here. So the star goes here, and then what goes after the star then? The variable name. I'm just going to call it like array because I'm super creative. Alright. So if you do this in your homework assignment, you'll probably lose points. Try to give it something more meaningful than just array. Like if you're working with the zoo example, call it the zoo. Like that's like more descriptive than array or section array. Anyways, so we create our struct student star array, which is going to be a reference to all the students. Now what do I do? Yeah. So now I need to start the allocation. So imagine I have 250 students. So 250 students, keep in mind. All right. So I want to do the allocation, so I can do array what? Name. Array dot name. Is that what I want to do? Like, what do you mean name? Do I put the word name here? I don't think I want to create the name. So the thing is, each student, so if you like look at a student structure, like imagine you had some box that was a student. The student has members inside of it. The members that it has some GPA. And that's going to be like some floating point value, like maybe 0.01, maybe they're a very good student. Oh boy. And then they have like some name. But the name is, what's the name? Out of curiosity. It's like, it's a string, but like, it's not like your standard static strings, right? Is this going to be like an array of characters here? What is this really, yeah? It's, oh sorry, what's that? Yeah, I guess it's like whatever we input into the computer, but like the type is going to be, I think I heard someone say pointer. What do you mean pointer? Is it a void pointer? Is this a void pointer? It's a char pointer. So this is really a pointer, and not only is it a pointer, but it's a pointer to some array of something. What's the array going to be of? It's going to be characters. Oh no, I'm the person with the bad GPA. All right. All right, that's sad. But the idea though is that this is going to be an address. So this is going to store some address that is going to like point to where the name is going to be stored at. Are we comfortable with that? Maybe? Maybe, okay. So, but the idea is, this is going to be one student. But the thing is, we don't make one student though. What are we actually making? We're making an array of students. So what we want to have is really all of these guys are boxed together where this is some student with some GPA and some name, and that name's going to point somewhere. And then this is another student with some GPA and some name, and that's going to point somewhere. And then like we're going to have this, like a whole bunch of things are going to be pointing to these guys. This is like kind of a, you can't see it, but this is really a 2D array that we are making here. And the reason why it's a 2D array is because this whole thing is an array, and each of these are going to be pointing to some array as well. But that means that if this is an array, in order to access it, what do we need? We need a pointer. So we need some pointer that's going to point to this. And really that pointer is going to be our array. I can spell. So that's the array in the main function, and that array is going to be pointing to the first student in a block of students that's going to have that information. So we don't want to do array.name or array arrow name here. And the reason why is because we haven't even created the students yet. We need to create like the list of all 250 students. This is a pointer to a student, not really a student itself. So what we want to do here is set this equal to something. What are we going to set this equal to? Yeah.
Are we going to start to dynamically allocate space?
Yeah, we're going to start with a dynamic allocation of space. Yeah. Is it going to be char? Is that the type that is the array?
Would that be struct?
It's a struct. But what type of struct is it? It's a student. It's a struct student. So this is struct student. Is that it? Star. Because that's the type that array is. Array is this type. And now, how do we create this memory? What do we do? Calc. Yep, 250. Why 250? That's how many students we have. Very good.
Size of
Yeah, so then we do size of struct student. Because that's how big each one of these students are going to be. Every student is going to be the size of a struct student. If you look at my terrible diagram I've done here, all of these blocks here are the size of one student. They have a GPA and a name, a GPA and a name, a GPA and a name. Every single one of those is going to be this. And you're thinking to yourself, is the computer going to be able to do this? And the answer is yes. The computer will know how big the struct student is because you've written it in your codes somewhere, hopefully. If you didn't write it in your code, then this isn't going to compile because it's going to know what the heck you're doing up here as well. So yeah, we want to go ahead and make sure we declare a struct student hopefully above, And then like the idea is that it will go ahead and say, oh, I know how big this is because it has like a double and it has a pointer in it. It's going to be the size of basically those of those combined together, and it'll go ahead and create all that for you. I've seen students that are like, oh, since the struct student has like a name and a double inside of it, we want to do the size of the name and the size of the double. Don't do that. That's a really bad idea. Technically, it'll probably work, but it's just not good practice. It's better to go ahead and just use the struct instead. Is there any questions on this so far? Yeah, in the back.
Oh, in my intro to C class, we learned how to use structs with type def. And
Yeah, so if you want to use type def, you can. That'll make your life a lot easier. You don't have to put the word struct everywhere. So the way I like type defs, and I'll go ahead and like maybe clarify this right now. I guess that's a note. So for type def. So how I like to see type def done, and if you do it differently, I'm not going to take off points, but it'll make me sad. I like to see something like type def struct student, and then you'll do student, and then closing like the semicolon, and then you go ahead and define your struct student later on. So you do something like struct student, can't spell, student, and then you go ahead and put like your definition in here. So this is going to be like a double GPA, and then a char star name. So I like to see this in your code. Now, when you're doing the type def, if you begin using the word student here, that will work just fine. So you can use the word student here if you've done your type def, and like everything will be good. So like somewhere in your main method, you can do something like array is equal to student star Malloc 250, and you can use size of student. And that will definitely be shorter code if you want to do it, no problem. Some people put the type def here, and those people are monsters, but yeah, I'll let that go. Do you have something to add, Jim?
Yeah, I do with that.
You're a monster then. Yes. That's okay. We're all little monsters or something like that, right? All right. So let's finish up this example. So hypothetically, we give the allocation of them. How do I get rid of this information at the end? I should free it. So the idea is I want to do something like free, and you do like array down here. Of course, since the name is supposed to be statically created, let's go ahead and actually do the allocation. So I'm going to go ahead and show you, I'm going to make every name of size 1000 plus 1 because names can be big. So it's going to look a little bit silly. We're going to do for int I is equal to 0, I is less than 250, I plus plus. All right? So we're creating 250 students, and each student is going to have their name assigned at this point. So how do I create the name then for the ith student? This is a good question. Let's imagine we don't have to scan it in. Let's just imagine we create it. So we're creating it. How do we do that? So I'll start you off. Array. What? Array bracket I. Very good. Dot name. Why not arrow name? It's not a linked list. All right. So not exactly. So when you want to use the arrow is when you want to dereference your struct information. So if you're given a pointer to your struct, you normally want to use the arrow. So then the question is, well, why, if we have a pointer to the struct, why aren't we using the arrow here? Because it feels like, we have a reference to the struct, and arrows are used when you have a reference to a struct. Why are we not using the arrow at this point? Does anyone want to answer why we're not using the arrow here? Yes. Is it because the name is already a pointer? It's not because of the name. It's because really of array here. So what is the array type? The array's type is a what? It's a pointer to a student, right? So the question is, well, if array is a pointer to a student, why don't we use the arrow name here? Yeah. The brackets already remove the star. The brackets already dereference. We don't need to use the arrow at this point because by using these brackets, we are now working with not a struct pointer anymore, but just a normal struct. So these brackets do the dereferencing for us. All right. Then we need to do set equal to something. What are we going to set equal to? So I'll go ahead and put a note. Brackets derect the pointer for us. That's the reason why we don't have to use the arrow operator. All right, so then I didn't give myself enough room, but we do array at I.name is equal to something. What should it be equal to? Char star. All right, and then what? Calc. And I said I'm going to give each one of these guys size 1,000, so it's going to be 1,000 plus 1 size of char. And that would be the allocation for this name. Of course, you really should make sure that you loop in free here before you do the free here. So for, and you want to free, what are we going to free here? Are we going to free array at I? What do we want to do? We already freed array here, but like we need to do a for loop free because we did a for loop free here. So what's that for loop free going to be? Yeah?
Is it array I at name?
Yes, we're going to do free array I's name. So we're going to do free array I dot name. And it makes sense because we created the name here, so we want to free that same name in this position here. All right, is there any questions about this? Yes. You could do them in the same for loop, but really that's kind of silly. Why would you be freeing the same thing you're allocating like in the same loop? Normally, like the idea is like you should really like create all your memory, do stuff with that memory, and then free it at the bottom. So I was just like, I didn't want to do stuff with the names because that's not the important thing. What I really wanted to do is I want to show you how you create that memory in the first place. Yeah, and then yeah, you do the for loop to create everything, and then afterwards, like at the end of your program, you do a for loop to free everything, and then you free the whole array at the end. What's your second question? Why do the brackets dereference? It's because when you're working with like a sequence of values, again, like in order to have like a sequence of values, like to know all the values in that sequence, you know basically where the first value's at. So the array is really going to always be a reference to the first section of memory for your list of values. So like you have a reference to that section of memory, and so the idea though is if you have a reference to a section of memory, the brackets will go ahead and go to that section of memory into the correct position offset by that I value. So when you go ahead and do bracket I, you're really going into the array, and then you're moving over I positions to where that section of memory is at for your array. And so we don't need to do another dereference because the brackets naturally will do a dereference to get to the correct position of memory. So if you have a pointer, which really is an array, by using brackets, you'll dereference it and go to the correct value. But like if you do just like, you can technically do like plus I, and plus I will be a reference to that section of memory, but won't actually give you that value. So in order to get that section of memory, you have to do a star at that point. So for those of you that are uninitiated, I'll show you some really horrible things, and this is stuff that you really should have seen in your C class. But if you do something like array at position I, this is the same as doing array plus I to basically move over I positions into your array, and then dereference it. These are the same. Also, because addition is kind of like commutative, which means you can swap the sides of them, and this is something that really disturbs me, and it'll probably disturb you as well. This thing here is also the same, don't laugh, this is the same as I bracket array. Alright, so let's never talk about this again. Does that clear things up? Alright, no problem. So, I feel disgusting. Alright, so something else I want to talk about in terms of structure allocation, just very minor. A lot of the times you have to do a lot of effort when you're doing allocation for like or initialization for a struct. It's a good idea sometimes to have something that will create that. Like there could be times where you have to make many structs in your program. And it might not be the case that like the struct creation is like you're storing them in an array. It might be that you want to get a reference to them. This will come up a lot when we're doing like linked lists and we're doing binary search trees. So sometimes what we want to do is we want to create a function that will create dynamically a single struct. So there's sometimes single struct creation functions that we want to create to implement. So single struct creation functions. And I'll just kind of show you an example of what those will look like. And these will probably appear on the foundation exam, and these will probably appear on my exams as well, so it's a good thing to be aware of. Like, if not now, then at least when we get to them. But I want to cover them now just so that way it's not going to be as confusing then. So, like, let's say that we wanted to make a something simple. We'll do a struct animal. All right, and we'll do like maybe it has like an int legs, and then maybe like an int age or something like that. I don't know what you need to have, like whatever you need for your animal. So the struct function creation thing that we have, and it could be like the following. So struct animal pointer, because we're going to return an animal pointer from this function, and we're going to call this create animal, and we're going to do int L. I'm actually going to do legs because I don't like using single variable names, and then int age. Why did I do a semicolon? What's wrong with me? Comma, closing parentheses. All right, so we'll pass in basically the two pieces of information that's important for an animal, and the idea is that we're going to create that animal and return it to whoever called us. So what we'll do is we'll do the following: curly brace to begin our function. We want to create a single animal. How would I do that? If I'm doing this dynamically. Anyone? Yeah, so do I just immediately call calc here? What do I want to say is equal to this calc? I don't want to just call calc without storing it in something, because that creates a memory leak. So I want to create a struct animal of some kind. So struct animal, and we want to say like, I'll call this ret. Why do I call it ret? Anyone? Yeah.
Return.
It's the return, yeah. So this is going to be the return. All right. And then what do I do with this ret then? Yeah, you have something to add?
No, you got it.
Okay, I thought your hand was up. All right. Yeah.
You said red equal to calc.
So we want to do ret is equal to calc?
Red is equal to struct animal star.
Uh-oh.
Oh, no, sorry.
All right, so I think you've noticed like a problem that we have here, right? What's the problem that we have here? So if I do struct animal, do we have a problem? What issue do I have if I do struct animal? Yeah? It's not a pointer. So the thing is, we'd be trying to take something that's supposed to be a pointer and assigning it some value. That's very, very bad. Please don't do that. So then there's something wrong here. We can't actually do ret is equal to those things based off of what's happening. So what do we need to do instead? So I want to make this a star, but if I make this a star, then what does that mean I've done wrong? So we need to put a star here because this wasn't the correct type. This wasn't actually a struct animal star. This was just a struct animal. So I need to actually make that a reference. All right. And then what do I do now? So yeah, now we can continue like normal. So we do calc. Yeah, so we can do size of struct animal. All right, that's a long line. All right. Oh, I missed something, right? What did I miss?
The size of whatever.
I need to say the number of things. I need to do 1 comma. Because I wanted to do only one animal. Yeah, do 1 comma size of. Because I need one animal, and that's going to be the size of the thing. Because the idea is this function is going to create just a single struct, and it's going to give it to us, and we'll be able to use it hopefully later. And this would allow us, if we wanted to, create like an array of animals, where we just keep adding animals one at a time. We don't necessarily know how many animals we want, but we know that we can create as many of them as we need. All right. And then what we can do is what? Like, how do we finish this off if we're trying to like initialize this information? Do we do, like, I want to update the legs and the age information, right? So I do ret what? Do I do dot legs? Is equal to legs? This won't work, unfortunately. Why doesn't this work? In the back? Yeah?
Because it hasn't been dereferenced yet.
So the problem is this is not an animal. Red is not an animal. You can only use the dot if this is like a struct. This is not a struct though. What is red? It's a pointer. And because it's not a struct, it's a pointer, we can't actually get the information out of it. So we need to do something to it first. What would we really need to do? We need to dereference it. Very good. So we could do like a star ret dot legs, and that would work. But doing star ret dot stuff is really disgusting. Like that, we have to go everywhere we want to use a struct pointer. So we have an operator that helps us out with this. What's that operator? Yeah? The arrow. So this is like where we want to use the arrow. So we want to do arrow, and we do legs instead. Don't use the dot. Don't use the dot when it is a pointer. If it's a pointer, you normally want to use the arrow. If it's just the struct animal, then you can use the dot. You do dot like legs at that point if it's a struct animal. All right. And then how do I finish this up? We want to return it. Don't free it yet. I want to update the age as well. So I do ret arrow age is equal to age. And then we'll return this information at the end. We'll do ret return ret. And then that way we create the animal. And now what we need to do is, yes, we would want to make a function that would destroy this animal, which sounds horrible. But it would be very important if you're creating a lot of memory in here. Thankfully, we don't create a lot of memory in here. Hypothetically, if we were creating like a name and other things, then it'd be nice to go ahead and like have the things like constructing that and like storing all that information inside here. And then the idea is we would, when we call our destroy method, we would go ahead and free up all that information we created. So if there was a name, we would free it. If there was like some like maybe hierarchy or something like that, that like some extra information had, we would go ahead and destroy it at that point. And so like with like more complex structs, it would be like more interesting. But this destroy is going to be very simple, very easy. So we're going to do a struct. Actually, it's not going to be struct. This is going to be a void. This is going to be a destroy animal. The destroy animal doesn't need to return anything because it's just going to destroy whatever it's given. So the destroy animal is given, it's normally given like a pointer to the animal that we're destroying. So we're going to destruct, and it sounds really brutal. Animal, pointer, basically to free, because we want to get rid of it, or to destroy, however you want to call that. And in this case here, what's the only allocation we did with the animal? Did we actually allocate legs and age?
No. Oh, we just allocated red.
We allocated the actual pointer itself. So this is the pointer, the to free. So all we need to do, this is a really simple one, we do free, to free. And that would be a single struct deletion function, or destroying function, or freeing function, whatever you want to call it. And then the idea is like whenever you created an animal, subsequently you'll hopefully destroy that animal in the future. All right, any questions about this example? It's supposed to be kind of simple, yeah.
Void destroy also the curly bracket that you have there?
No, it should be out of the curly bracket. So like it's not in the curly bracket. So this function would not contain this function. It would be two separate functions. We're good? Yeah.
And then just to clarify, to-free would just be the variable that rest would go into?
To free would be the variable that holds the address of the animal we created. So yeah, ret would eventually be the same address that the to free would be. Okay, so now I want to talk about something that I sometimes see people do, and I just want to clarify. There is something called typing in this language of C that's very important to acknowledge and to be careful of. So if you have something like, let's say we have something like struct student, all right? And you do something like char star name. All right, what I don't want to see you guys doing is the following. Don't do not, in your main method, say something like struct student Bob is equal to calc 10 comma size of chart. I know this is tempting, it's not good. So what issue do we have here? In the back, I saw a hand. Yeah?
Yeah. Does that work? Because like
No.
yeah. What if
Okay,
you do
this
like
doesn't work.
struct student dereference Bob to then typecast the char pointer or the char star?
So we would need to, like, if we had Bob, we would actually need to really access Bob's name if we want to do an assignment here, because, like, you know, that's what we're really creating here. We're creating like a string of like 10 characters, and the name was the 10 characters. So just because the struct student holds like the char name, that's really all that there is to it. This doesn't actually work really well. Don't do this. This is not good. We would really want to go ahead and first create Bob and then assign its name to the thing we're creating. And the reason why is because what is the type Bob? Bob is a student, right? What are we trying to turn this into though? What's the result of Malloc turning into? It's turning into a char star. Those are different types. Those are like apples and oranges. You can't really compare them to each other, especially in this problem. Like, make sure that when you're doing your assignments, you're assigning things to the correct type. Make sure that, like, even if you're using structs and it looks like the structs is like kind of like obfuscating something into something else, you're like actually doing the proper assignments of one type into another. It's just like a good thing to avoid. All right, I have a little bit of time left, so what I'm going to begin doing is I'm going to begin talking about something called a binary search. Woo! It's going to be fun. Finally, this is what I'm supposed to talk about. All right. So has anyone ever heard of binary search before? Like, raise your hand. All right, a few people aren't asleep. That's good. So if you haven't heard of a binary search, don't feel bad. Does anyone know? I can't really ask a lot of things because unfortunately we haven't covered analysis. So we'll talk about the common example that comes up with a binary search. We'll talk about the dictionary example. I didn't talk about the array list. Do you want to talk about the array list? Damn it, you want to talk about the array list. All right, I'll cover probably the binary search next time. I want to talk about one nice data structure before going over that. All right, so one last thing with dynamic memory. I'm sorry, we're still going to be on this for like another year. So the array list. Yay. All right, so has anyone ever heard of a list before? Let's go with that. One person, cool. 2 people, 3 people, 5, or 10, cool. All right. So a lot of you guys have heard of lists. What type of list have you heard about in the past? Yeah, in the back. Linked list. Yeah. So what's a linked list? Can someone explain to me? Yeah.
It's like getting different structs, and like I guess it's like you're putting them in different. You're able to change the orders of them by assigning different addresses to the nodes.
Okay, so we have like some values that are in some order. That's what I'm getting out of this. That's kind of what's a list. Does anyone know like what's different between the array list and the link? Like, how about what's in common between the array list and linked list? Does anyone know what they have in common? Yeah, in common. So they're both lists of values, but what does it mean to be a list of values? So they are some, like, how about instead of using the word list, because this is like a recursive definition that we have going on here, we'll call it like maybe a sequence of values. And we've worked with sequences of values, and see before we have the array, right? The array is a sequence of values. You can put them inside there. So why is a list any different than a normal array? Yeah. So if we have a pointer that points to the next, that's really actually going into the linked list perspective. So the linked list isn't necessarily the same as an array list. There is some difference, and it's kind of like hard to like really put your finger on it if you haven't like seen more list examples. But the main difference between this and an array, like between the list and an array, is that it's also unbounded. So is your normal array unbounded? If I create an array of like 100 elements, is there a limit? Yeah, 100, right? You can't go beyond that. But the thing is, I'm telling you that we're going to go ahead and create an array that is going to somehow be unbounded in a weird way. So when you have a linked list, it's pretty easy to see that it's unbounded, because if you know how a linked list works, they have these pointers that point to the next node. What you could do is you could always just go to the end and create another node there, and it could keep going on forever. And you can keep creating more and more nodes, and you can do that all dynamically, and everything is fine, hunky-dory, no problem. Now, the thing is, when we're doing an array list, when we create basically a section of memory, it's going to be limited. It's going to have some capacity. And what's going to need to happen is when we try to go beyond that capacity, we need to do something. So what are we going to have to do if we try to go beyond the capacity of an array? What could we do to make it so we could keep going on? Yeah?
Have a structure point to itself.
So, okay, we could have a structure point to another structure of the same type, but then the thing is we're getting into a link structure. We're going to try to avoid links. I want to avoid having a struct point to itself if possible, but yeah, that would be possible. That's unfortunately the linked list. I don't want to do a linked list though. I want to use an array. I want to use, if anything, I want to use a single pointer. So the goal of this, because I'm using an array here, I want this to be one pointer if possible. So this is crazy. How do I do a single pointer? All right, I haven't talked on ecology too much. Allocate more memory. And so how do we allocate more memory? Like, what do we use to basically create a section of memory that's larger? You got something in the back? What? Reallocate. So what we do is when we fill up, we just reallocate to make it bigger. So I'll go through kind of the highlights of how an array list works. We could use a structure to go ahead and create the information. We'll go ahead and create a function that creates our array list, and then you can create a function that deletes it, and it'll be a horrible example for us all. I'll actually code it up on the computer, and we'll watch it like crash and burn or something. All right, close that out. Well, not that one. We're gonna call this the array list.c. You guys can totally see that, right? You guys have binoculars in the back there? Try to make that a little bit bigger. All right. So count include standard io.h, count include standard lib.h. And to demonstrate this, what I'm going to do is I'm just going to add numbers until I add a -1. So the goal of this function is to read numbers from input until -1 reached, and then print numbers read at end. That's going to be the goal of this program. So we're going to make this array list. So I'm going to make a struct for it. So struct array list. And then we're going to do an int star array. And then we're going to do an int. And we need to do two things besides the array. So I want to use just one pointer, but I also need to know how many things are currently in my array. And I also need to know, am I full? So in order to know if I'm full, I really need to know how many things can I put in here. So I need to know both like the number of things that are in here, I'm going to call that size. And I need to know how many things can I put into here, so the capacity. So it's kind of like the capacity of a room versus the size of the party. The size of the party is how many people are there. The capacity of the room is kind of like how many people can fit there before we end up with like some fire marshal limit violation and probably the cops being called us. So what we're going to do is type def struct array list, and that will create basically the word array list is now struct array list. So anywhere I want to use the struct array list, I can just use that instead. We'll make a function. So these are going to be prototypes. We're going to do a creation. So array list star create array list. And then we're going to pass in nothing because we don't need to pass anything in. And then we're going to make a void function that is destroy array list. And that's going to take an array list pointer. And then we also want to make a method to add two lists. And we're going to do an array list pointer, and then we're going to pass in the value that we're going to be adding to the list. So let's go ahead and make the main method. So we're going to have our array list pointer. It's going to be, I'm going to just call it list is equal to create array list. So all I'm doing is I'm creating the array list. I'm now going to go ahead and read in the values. I'm going to say while one. What's while one do? It's infinite loop. Why am I trying to infinite loop here? Yeah, I don't want to do a fixed number. I want to keep reading until they basically tell me they're done. So I'm going to do scanf %b, and I'm going to read that into value. And then we're gonna say, if the value is equal to what? What do we do? What was the special value I said that allows us to exit? -1. So if the value is equal to -1, then what do? Break. Very good. And then otherwise we're gonna add it to the list, so we're gonna say add to list, and the value. And then we're gonna print out the values. Printing out the values is gonna be pretty easy. Print values. Ready for int I is equal to 0, I is less than list arrow size, I++. And that will basically go through every person in the party and allow us to name them off, because hopefully we learned all their names when we did the add to list. We'll do printf, %d, new line, and then we say list array at position ARR, at position I. And then we need to destroy the list. So destroy array list. Return 0. Clean up memory. Alright, now the horrible part, which is actually, the main method is done. This is all the main method is. You create, you read, you print, you destroy. That's how I live my life. So now what we're going to do is copy these 3 prototypes down here, and we're going to have to implement them. So the array list creation is pretty easy. We do array list star ret, because this is going to be the same thing as the animal that we did earlier. We do ret is equal to calc. Oops, let me do a count here. So array list pointer calc 1 comma size of array list. What we're going to do is we're going to set the size. How many people are in my party to begin with? 0. There's no one there at the beginning. What's the room size going to be? Initially. The answer is whatever I want. I'm going to do 10. And then we need to go ahead and create the room itself. So we're going to say array is equal to, we're going to do int star calc, and it's going to be ret cap, comma size of what? How big does this need to be? What is array? Array was an int array, right? So how big does each element need to be inside of it? If it's an int array. Inside of it. Alright, and then we're going to return the ret. Alright, destroying the array list is going to be pretty easy. All we need to do is just say free, like 2 free, and that's wrong. Why is it wrong to just do free, 2 free? What did I miss? I did. I just did it here. Okay, what did I do wrong? I typed it up while you probably weren't looking. That's fine. What did I do wrong now? I didn't free the attributes. So there was one attribute, the array, that was created that wasn't free. So what I need to do is I need to say free, like 2 free ARR. Alright, and unfortunately, that is kind of all the time I have. I will finish this up next time. It's officially 6